This is the second week of our AP Physics class, and we're going to continue Unit 1, which is called Kinematics. Moving on to the second week, and then our agenda for today is acceleration, so we'll be looking at that. Our lesson objective for the day is to be able to express acceleration graphically, mathematically, and also as a narrative, as a description. So let's go ahead and get started. What is acceleration? Acceleration is the change of velocity of an object over time. Acceleration is calculated by this formula right here, where A with a line on top is the average acceleration, which is the change in velocity over change in time. Now, change in velocity is velocity final minus velocity initial, and the change in time is time final minus time initial. Now, looking at some graph, here they give you a velocity time graph, also here another velocity time graph, and they point out the fact that the slope of the line tells you the acceleration. So in a velocity time graph, the slope of that line tells you the acceleration. Here we have a positive slope. That means our object is accelerating. Here there is no slope. So that object is holding its velocity, but it's not going any faster. It's going to keep a constant velocity. It has zero acceleration. Next, the object has a negative slope for the graph, so therefore the object is slowing down, so it has negative acceleration. Normally people say it is decelerating, but in physics we're going to say it has negative acceleration. So it says in a velocity time graph, the slope of the line is acceleration. Moreover, the y-intercept is the initial velocity. In this problem, our problem begins with an initial velocity of 0. For our second problem, we're going to begin somewhere around -11. The area under the line is the displacement, which is how far from the origin we have traveled. Alright, so we've talked about this first graph. Let's talk about the second one. In this graph, if I were to use my pointer as an object moving, I would begin by, well, it's got a velocity of 11, -11. In physics, usually negative is towards the left, positive is towards the right. So it has and it's a flat line, it has a constant velocity, so my object will be moving at a constant velocity in that direction. Once it reaches this point, notice the slope of the line is going towards 0. So it is decelerating, or it has negative acceleration. So our object was going at a constant velocity, and now it's going to begin to slow down and come to a full stop. Right at this point, notice the velocity is 0. That's where our object reached a full stop. Now it's going to have positive velocity. That means it's going in the positive direction. So our object is now moving in the opposite direction. It's going to speed up. That's this first part of the line. Now it's flat. It's going to maintain a constant velocity. And then finally it's going to go ahead and come to a full stop after slowing down. So have negative acceleration there as well. So the graph can give you a pretty good indication of what the object is doing. Now in a motion diagram more or less gives you an idea of what is the object doing. Is it going at a constant velocity like our first, the car right here on top? Notice that the gap in between the vehicles is the same. That means that that vehicle is holding a constant velocity. Next, for our second line, the gap is getting wider and wider and wider. This vehicle is increasing in velocity, so it is accelerating. So the velocity is going higher and higher and higher. The last one, the gaps between the vehicles are getting smaller and smaller. So you can say that car is slowing down, so it has negative acceleration. So we don't say deceleration, we have negative acceleration. Alright, so let's go to move on to our first problem. Problem number 3 says, draw a position time graph, velocity time graph, and acceleration time graph for the diagram below. So let's go ahead and do that. So in this diagram, we have the car, and notice that the gaps are the same throughout. So I can look at that and say that vehicle is moving at a constant velocity. I'm going to draw a free body diagram for it, and this is problem number 3. And a free body diagram, that means I'm not going to take the time to draw the whole car, just put dots in its place, and should be about equally spaced out. So again, the first one that they want is a position time graph. Alright, and a position time graph, we're going to have here x as our position and time. So what would that graph look like if the vehicle is constantly moving? Well, you would get a diagonal line as time's going by, the vehicle is moving. So that would be your displacement time graph or position time graph. Next is a velocity time graph. So I'm going to put velocity here, time right there. What will that line look like? Well, it is going at a constant velocity. So what would that look like? It would look as flat line, but it's got to be somewhere above zero. Anywhere above zero. We don't have any numbers here off to the side, so anywhere above zero, that will do it. Alright, so that will be a velocity time graph. The final one, an acceleration time graph. This car is going at a constant velocity again, so it's not really moving, it's not accelerating, so it has zero acceleration. So we need a line with a slope of zero. It's got no acceleration, so we're going to draw it right here where the zero is at. So that will be problem number 3. So it's your position time graph, velocity time graph, and acceleration time graph. Notice that I always put time on the x-axis. Let's move on to, there's the answer for this one. Let's go ahead and move along to the next problem. On problem number 4, they ask you guys, draw a position time graph, velocity time graph, and acceleration time graph for this diagram below. So they want the same type of graphs, but in this case, notice that the gaps are getting bigger and bigger and bigger. That means that our car is going faster and faster. It is accelerating. Alright, so when I here put problem number 4, and I'm going to put my free body diagram. First they're pretty close, and then the gaps are going to get further and further and further away from each other. So that means your car is speeding up. It is accelerating. So what would that look like for a position time graph? Well, you would begin by saying that, well, the line will start very flat, but as you get faster and faster, it will get steeper and steeper because you're covering more ground in less time. So what would that look like? It will be a curved line. See, at first, you're not going that fast, but then you're getting faster and faster and faster, so the slope of the line is increasing. Next, our velocity time graph. The velocity is increasing constantly. It's constantly increasing. So it is increasing, but it is constant. So therefore, we get a flat because it is a constant increase in velocity. Flat diagonal line because the velocity is going up and up and up, but at a constant rate. Finally, the acceleration time graph. For that one, we're going to assume we have constant acceleration. So it has to be a number bigger than 0 because we are accelerating, but it is constant acceleration, so we're going to leave it flat. All right, let's move along to problem number 5. In problem number 5, they ask you guys, draw a position time graph, velocity time graph, and acceleration time graph for the diagram below. In this case, our vehicle is slowing down. It is decelerating, but again, we don't say that in physics. Instead of decelerating, you say it has negative acceleration. All right, so I'm going to go ahead and put problem 5 here. Again, we have our displacement or our position time graph. And what's happening to this vehicle? Well, as time goes on, it's going pretty quick. So we have a pretty steep slope, but then the slope's going to curve. Why? Because now you're covering, as it slows down, you're covering less distance over longer periods of time. So that's what it would look like. We're going to go ahead and assume that it has a constant deceleration or negative acceleration. So therefore, for a velocity time graph, the velocity is constantly dropping. So it looks the same as that. And it is a negative acceleration. So what would that look like in an acceleration time graph? Where would be the negative acceleration? The answer for that one was actually below 0. That's our 0. So the line should be somewhere here. It would be the mirror of this line, but on the bottom, because it has negative acceleration. The acceleration is going against the vehicle. As a matter of fact, these green arrows represent the acceleration of the vehicle. And let me put the answers for that one. So there you have it. It's curved straight down, and on the negative side for the acceleration, because it has negative acceleration. All right, that takes us to the end of problem number 5. Now let's go ahead and take a look at problem number 6. Example 3. In this one it says, a bus starts moving northbound at 10 meters per second for 5 minutes. Then a bus stops at a red light for 1 minute. After the light turns green, the bus continues to travel in the same direction for 7 minutes at 12 meters per second. Calculate the average velocity of the bus. Alright, so for this problem, we're going to go ahead and solve for the velocity. But how do we solve for velocity? That will be question number 1. What do we need? Velocity is calculated by displacement over time. Alright, so that is, velocity is displacement, change in displacement over whatever time it took us to get there. Alright, so we need to figure out how far that bus traveled and in how much time. Alright, let's start with the distance that this bus traveled. Alright, so figure out the distance it traveled. We're going to break it up into 2 parts. First, it was traveling at 10 meters per second for 5 minutes. And next, it was traveling at 12 meters per second for 7 minutes. So we're going to keep those 2 separate. To get the displacement, I'm going to go ahead and get this t slider over here. And displacement is velocity times time. So I'm going to put the first part of the journey. What was it? First part of the journey, it was, as I mentioned, velocity multiplied times time. So it was traveling at 10 meters per second. And the time is 5 minutes. But as a matter of fact, I cannot put that 5 minutes. That would be a mistake. And the reason why it's a mistake is because you'll notice that the velocity is in meters per second. So therefore, I need the 5 minutes in seconds. Alright, so please watch out for your units. Alright, so it's not 5 minutes. Well, it is 5 minutes, but what's 5 minutes in seconds? That's 300 seconds. So for the first part of the journey, it was traveling at 10 meters per second for 300 seconds. So it traveled 10 times 3,000 meters. That's the first part of the journey. After stopped at a light, then this bus went ahead and continued for 7 minutes at 12 meters per second. Second part, same formula. Velocity times time is our displacement. So we're going to go ahead and solve for that. It is traveling at 12 meters per second. And again, that has to be in seconds. You cannot have mismatched units. And there's my calculator. Alright, so I'm going to multiply 60 seconds times 7 minutes. And that gives you 420 seconds. You go ahead and you multiply 12 times 4.2, 420. Gives you 5,040 meters. So what is the grand total for the displacement? So I would say, well, the displacement total is, well, displacement when it was moving the first time plus displacement when it was moving the second time. So that will give us, essentially, add both of these together, 8,040 meters. Alright, so now we have the displacement for the whole trip. How long did the whole trip last as far as time goes? The time, it was 300 seconds for the first part of the journey, 420 seconds for the second part of the journey, plus it does say that I spent 1 minute waiting, and that is part of the journey. So I'm going to put that in seconds as well. So that's going to go ahead and give us 780 seconds. Okay, so now we've got everything we need. We've got the time total that we needed to complete this journey, and we have the displacement total we needed. So therefore, to get the average velocity for the whole journey, it is displacement over time. So we're going to go ahead and divide. Both of these values. So it is 8,040 divided by 780. It gives us 10.3 meters per second as the average velocity for this trip. Alright, that takes care of example number 3. Now the follow-up to this is problem 6. In this one they ask us, can you draw a velocity time graph for the school bus in the previous example? Alright, so let's go ahead and take a look at that. Now, the bus motion, we're going to go ahead and display it as a graph, so in a graphical method. So that's what they want from us. Let me go back to look at what they have given to us. It was traveling at 10 meters per second for 5 minutes. So in our velocity, the bus starts at 10 meters per second and that lasts 5 minutes. So it's traveling at this velocity constantly for 5 minutes, that's 300 seconds. So I would draw a line there going at a constant velocity, 10 meters per second. And then at 5 minutes, that's when they come across the red light, so they have to stop. So what will be the velocity of the bus once it has to reach a full stop? Well, it's going to be at 0 right here. How long is it there? For 1 minute. In my time, I have it in seconds, so I went ahead and I'm going to put 1 minute. So that's 360 seconds. Next, the bus light turns green. It continues for 7 minutes at 12 meters per second. So I'm going to go ahead and draw a line and up here to 12. And it continues its journey for another 7 minutes, which was 420 seconds. So if we add what we already have here plus another 420 seconds, that'll give us 780 seconds. And that's the end of the journey. Perhaps I shouldn't even put that down because they didn't tell us what the bus did next. So that will be the end at 780 seconds. Alright, that takes care of problem number 6. Alright, now let's go ahead and move on to problem number 7. In this problem, they ask you as the following question. A car accelerates eastbound from rest. Now, anytime they tell you the car is at rest, that means that it is parked. Its velocity is 0. It's not moving. So a car accelerates eastbound from rest to 10 meters per second in 5 seconds. Then maintains the velocity for 30 seconds. Then slows down to a stop in 10 seconds. So part A, draw a graph of the velocity time graph. Alright. Part B, calculate the acceleration from 0 to 5. Calculate the acceleration from 5 to 35 and from 35 to 45. And then calculate the total displacement of this vehicle. Alright, so let's go ahead and start with part A, which will be doing the graph for this problem. So let's go ahead and graph this problem. So one more time, it says the car accelerates eastbound from rest. It's at rest, so therefore it is not moving, so its velocity is 0, and that's where we're starting from, right at that point. It begins to accelerate for 5 seconds and reaches a velocity of 10 meters per second. So at 5 seconds, it reaches a velocity of 10 meters per second. So I'm going to put a dot right there, and I'm going to connect both of those dots with just a straight line. We're going to assume constant acceleration. Then the car maintains that velocity for 30 seconds. Alright, so for 30 seconds. So here we're at 5. At 30 seconds to that will be a 35. So it says the car is going to maintain the velocity for an additional 30 seconds. So we're 35 seconds into this journey, 5 seconds to accelerate, plus 30 seconds of maintaining the constant velocity. Next, the car slows down to a stop in 10 seconds. So add from 35 to 45, there's your additional 10 seconds. And what happens is going to come to a full stop. So we're just going to do constant negative acceleration slowing down. And there we have it. So that's part A. In part A, they ask you, can you please go ahead and draw it? Alright. Next, they ask you guys, can you calculate the velocity, the acceleration from 0 to 5 seconds. Alright, so we're going to go ahead and do that. And the acceleration is the change in velocity over time. Okay, so acceleration, this will be B. In acceleration, we're going to go ahead and have the change in velocity. So it will be velocity final minus velocity initial over time final minus time initial. Okay, so essentially we're getting the slope of that line right there. That's the acceleration. A velocity time graph. The slope of the line is your acceleration. Alright, so we're going to start velocity final is here, and that'll be 10 meters per second, and velocity initial is there, 0 meters per second, over Time final took 5 seconds to get there, minus time initial 0 seconds. So it is just 10 meters per second over 5 seconds. So all you got to do is divide 10 divided by 5. Its acceleration is just 2 meters per second squared. The square is because there are 2 seconds in the denominator, so that's why it's second squared. That's the unit for acceleration. In part C, I'm not going to do the calculations because it's a flat line. What does that mean? It is holding a constant velocity. So therefore there's no acceleration. So part C, the answer is 0. I'm not even going to write that down because the line is flat, it's got constant acceleration. Let's jump to part D. In part D, they want to know what is acceleration from here to there, from 35 to 45 seconds. So part D, the acceleration is going to be same formula. Rather than putting this, delta means change, so final minus initial. So change in velocity over change in time. I'm going to use those symbols instead. They mean the same. Alright, so let's start with here. The final velocity is 0, and that happened at 45 seconds. So final velocity is 0, and it took 45 seconds to get there. And here, at the beginning of this line, it was at 35 seconds and the velocity was 10. So I'm going to put minus 10 meters per second, and that was at 35 seconds. Okay, so we go ahead and we solve for this. 0 minus 10 will give me a negative 10 meters per second. And 45 minus 35 will give me a 10 seconds. So our answer is negative 1 meter per second squared. Alright, why negative? Well, look at the slope of the line. It's got a negative slope. That means it is slowing down. It's got negative acceleration, so it's slowing down. Alright, up next, part E. In part E, they ask you, can you go ahead and solve for the displacement of this vehicle? And for this displacement, there's a couple of ways to go about it. But we're going to stick with what we started this lesson with, which said the area under the line is the displacement. In a velocity time graph, the area underneath the line, that'll be all of this, is the displacement of the vehicle. Alright, so how do we get it? Well, let's section it off. There and there. Notice you got one rectangle here in the middle and 2 triangles on the sides. Alright, so we need to get the area of the triangles and the area of that middle rectangle. So we're going to break it up into pieces. So we're going to call this guy number 1, this one number 2, and that one number 3. So we need to get the area for those 3 regions. Let's start with number 1. Now that is a triangle. So how do you get the area of a triangle? You know this from your math class. 1/2 base times height. So when you have an acceleration, the displacement, which I'm going to put here as delta x, x is on the x-axis, it's going to be 1/2 the velocity multiplied times time. Velocity is your height and time is your base for that region right there. So let's see, that will be, the velocity was 10 meters per second. And the time, it took 5 seconds. So you go ahead and you multiply. 5 times 10 is 50, times 1/2 is 25 meters. The seconds got canceled out. Alright, so that'll be the displacement for the first part. For the second part, that's this rectangle, notice there's no acceleration. No acceleration, that means it's just velocity times time. So if you were in math class and they asked you solve for the area of a rectangle, you know it's just base times height. So that will be our second region right there, which is velocity times time. The velocity is 10 meters per second. The time, it went from 5 to 35, so that's 30 seconds. So that gives us a total of 300 meters of displacement. Finally, for our third area, it is a triangle. There is deceleration, so I'm going to put again 1/2 base times time. So it's going to be 1/2 the velocity. Velocity was 10. And the time went from 35 to 45, so that is a 10-second difference. So 10 times 10 is 100, times 1/2 is 50 meters. Alright, to get the grand total, you would add up all three areas, right? So I'm going to put delta x with a t for total, which would be delta x, the first area, plus the second area, plus the third area. Alright, next substitute the numbers for it. It is 25 meters, plus 300 meters, plus 50 meters, and gives you a grand total of 375 meters. That will be the displacement for this problem. There are other ways of solving this, and we'll save those for later. For now, just know this. The slope of the line is the acceleration. In a velocity time graph, the slope of the line is acceleration. And the area under the line, that is your displacement. Alright, let's go ahead and move along to our next problem. This one will be problem number 8, and it is the last one for this section. It says, draw an acceleration time graph for each of this velocity time graph. Alright, so let's do those. So, they give you the velocity, and they want you to interpret, okay, from there, what will be the acceleration? Alright, so we have, how would you describe this velocity? It's a straight line. So, therefore, it would have, well, the velocity is constantly increasing. It has constant acceleration. So what would the acceleration time graph look like for this one? It would be a flat line. That is for the first one. For the second one, notice that the velocity starts off slow, but it gets faster, and then it gets faster, and it gets faster. So we got a curve right there. So therefore, we are increasing in velocity. So if our velocity is getting faster and faster and faster, then we must be increasing our acceleration. All right, so that's what the acceleration would look like for that velocity time graph. And our last one is a little bit of a trick question because it's got two parts to it. So our velocity time graph, what will be the acceleration time graph for that? Okay, well, let's take a look at the first part. Notice it's going straight up. So what's happening? Well, just like this one, we have constant acceleration. So it will look like that up to that point. And then what happens to the line? The velocity remains constant, so you're no longer accelerating. Now you're just holding your speed. So no acceleration, then it will drop to 0. And that would be the answer for that. Alright, that is problem number 8 on our acceleration lesson, and that is the end of our lesson. And thank you for watching.